All right, great. Let me begin then. Jason Corso here, professor at Michigan, working at the boundary of humans, computers, and AI, and also now the chief science officer at Voxel 51, co-founder, was the CEO for the first 5 or so years. And as we grow our company and sort of broaden our base, so glad to be initiating this new science effort. So the talk today is about human and AI collaboration, which is a topic I've been interested for decades. I'm in my mid 40s, probably about 40 years when I realized that there were humans, that they're computers and they were different things. And I have to thank my students, past students who are listed on the bottom of the slide here, and scientists and so on, whose work contributed to a bunch of the material in this talk. So this is all about the notion of inference and whether or not one should trust the human that they're working with. So, you know, watching sci-fi, reading the news, one might imagine that we have already today AI partners or collaborators that might be depicted in ways that you see in this graphic, right? Like, we work together, we understand each other. When I don't understand something, then my AI completes my sentence and so on. And it's a dream. It's amazing. We really want this. And for me, it got started back in the 80s when the Nintendo system came out.
Witness the birth of the incredible Nintendo Entertainment System, the one to play with Rob, the extraordinary video robot, batteries not included. He helps you tackle even the toughest challenge. Will you be the first to raise the incredibly accurate Zapper and play games like Duck Hunt or action-packed Hogan's Alley and high-flying Kung Fu, each sold separately? Will you be the one to experience the Nintendo Entertainment System?
So, I watched this commercial. I don't know, I was like 8 or something like that. And I was over the moon excited about this new like life form that was going to be playing games with me. Uh, and then I went to a friend's house who got the Nintendo system, and the robot was so terrible that they actually had returned it. And all they had was that gray box in the back, which is the actual console. And, I obviously had a ton of fun with the console, but like this promise of like this partner that was going to do things with me and interactively and help me, and like I was going to help it, and we were going to solve tasks together. It's just that it's a promise, right? Like we're not there. We're really, really far from that. Like even this system.
No, it's just sorry to grab the chip back.
Entering out chip bank.
So this is like essentially a state-of-the-art mobile manipulator that I did, that was done in my lab with myself, some students, and also Brent Griffin, actually, who's on the later going to talk later in this session. Looks pretty simple, but actually state-of-the-art. Won numerous national competitions against teams at Stanford, MIT, and so on. Like this was funded by Toyota Research, and it's great. It's a lot of progress, but it's far from the imagination that I brought, that we see in sci-fi movies, even to, today, for example. We've gotten a little farther than that as well. This is an example of a project in my lab called Robot Slang, in which, two agents, either humans or AIs, are cooperating in kind of like an Amazing Race type project, or type task. So there's the driver who can control the robot. You're seeing the driver's view on the left side here. And that's all they can do is they see forward and can control the robots forward, backward, left, right, and so on, and then have a text channel to the other agent, the commander, who has the map, but it's a static map, not a dynamic map. The view on the right they don't see the view on the right. It's just like a static instance of that. But they do know where the goals are, right? Like the bottle of blocks or the coffee mug and so on. And they have to use that text channel to communicate effectively to find the goals, as fast as possible. This was published at Corso a couple of years ago, and it's kind of like a benchmark for language-based interaction between humans and or AIs in a mobile robot platform. But these are just instances of like human AI collaboration, right? Something that in my lab we call hybrid intelligence. So how can we integrate human and AI systems during the full life cycle of an AI method in a way that facilitates the best of both worlds, perhaps, right? Like humans are good at some things and AI systems are good at other things. there's a little bit of an overlap, right? The Venn diagram is not completely disjoint, but at the same time, we are good at kind of different things, right? Like AI systems are good at, nuanced, detail-oriented, repetitive tasks that can be trained and don't have much variation, right? Like humans can do these things, but they tire and they get exhausted and they make mistakes and they don't necessarily do them as fast as they need to do them, right? Whereas like human systems, they're really good at mess, like change, where the state space from the what you learned on is very different than the state space that you're actually operating in, right? Or like dynamically operating in, right? Like here is a picture where you might need to find the Christmas ornaments, and this is like late fall or something like that, and you need to find them and put them out on your front lawn, like. Not something I want to go tell my home robot to do because they're just not really adept at this type of adaptation, right? In this direction of work, we are looking to consider different scenarios in which humans and AI agents are working together, and they might be cooperating on the fly during inference, rather than the more classical scenario where, like the human is available at the beginning to label the data, and then that labeled training data gets passed to the computer system, the agent in some way, who trains it and then runs in a closed loop and just on its own without any further interaction, right? Which is by far the dominant way of doing, supervised AI these days, right? So in this case, consider this retrieval task, right? Like the underlying goal is that this elderly gentleman wants his home robot to bring him his mug from the table over to him so he could have a cup of coffee or tea or something like that, right? So he says, "Please fetch me the orange mug." And the robot goes and fetches the orange mug. It's a very clear and concise prompt, if you will, to use contemporary language. Right? This is sometimes called preferring expression in the machine learning literature, right? So you look at an image and you accept some prompt or like in the form of a natural language expression. I guess it could be some other type of expression, but let's just assume it's a prompt, language prompt right now. And then you go and identify the object in the scene, right? Like in this case, here's the image as an example. The prompt is something like write yellow mug. And then we have some task model that term will come up a few times throughout this talk. And then we get hopefully get the right answer, right? In this case, there are two yellow mugs, so there is some ambiguity. So the notion of right is important for the task model to be able to incorporate into the output. Left coffee mug might get you a different one, right? As an example. This type of task is like significantly more involved than, say, de facto object detection from however many years ago that was like the state of the art in computer vision, right? So like we've definitely made some progress in these multimodal problems. So imagine, these evaluations are getting 91% accuracy, brings you a lot of hope that we're almost there, right? Ready to solve the problem. But at the same time, this 91% accuracy is really under standard assumptions that it's like supervised learning, there are no mistakes in the data, that the information is sort of semantically meaningful, and that the prompt is sufficient to disambiguate the expression, right? Imagine, for example, that the two mugs were not like sort of left and right on the scene, but they were like top and bottom, and the prompts didn't change, right? The right yellow mug and the left yellow mug. When might this be the case in reality? Well, the agent may be looking at the scene in the way I described, right? Like the two yellow mugs are top and bottom, but the individual prompting the agent may be looking at it from a completely different angle. And so right to the individual is top to the agent, and left to the individual is bottom to the agent, and we're hosed. We can't solve the problem. What do we do now, right? Like that's like a concrete instance of why AI is hard, right? That's why there are no cars on the road that are autonomous yet. Like that's why AI is hard. It's like the actual physical realization of these proxy problems makes it quite difficult, right? So this is something, however, like the correctness or like the confidence we've been building in the field is based on something that in my group we've been calling the Oracle assumption, right? This notion that all human provided information is semantically correct, unambiguous, and equally valuable. That's kind of like a core assumption that we have in the work. Not just us, like in general. Like that's like this, all of supervised AI or supervised machine learning is based on that assumption. In seated inference, it kind of looks like this, right? You have an input on the top. There's some fixed input, like an image. Let's call it X. Some human provided input, like a prompt, or what we called it, before prompt became popular, was a seed. And then there's some task model that can, compute some conditional probability for some task space Y given or conditioned on X and H that's mapped to some function, functional representation like F, right? And then we have during training time, we have some loss function L on Y hat, which is predicted versus the ground truth. And we need to have that ground truth to actually constrain the function F and learn the parameters of it. So as another example, the prompt here might be the second hydrant, and the task model is able to leverage that we wanted to leverage it's the second one, I guess, from the front, but it could have just been the second one from the back as well, right? There's a lot of semantic ambiguity in these problems. And that comes out in other scenarios, right? Like here, left banana, where the actual prompt is more meaningful in my view than the prompt on the hydrant case on the left, but the task is a lot harder, right? Just from a visual standpoint, right? So the task model actually gets confused. So this is not like we're not the first to look at seeded inference or prompted inference, if you will. This is, decades old type of problem. I think we kind of put a bow on the space of seeded inference problems a few years ago when we began writing this work. But this notion of single target visual object tracking, where you have a video, and on one frame of the video, you have a bounding box around the object you care about. Supervised video object segmentation, where you have a video again, and in the input is one frame that's like a actual pixel-wise segmentation of the object that we want to segment, or VQA, or referring expression, like I was just telling you about. Right. So let me give you an example of human and AI interaction under an oracle assumption. This was a paper we had at ICCV 2017. I won't have time to talk about the lower one here, but just to give you a sense, like this is not a paper in isolation. There's quite a few different examples of this, right? So in this case, we were looking at an autonomous vehicle scenario where obviously realistic training data is vital to the success of AVs, right? Especially in those rare events where like there's a near miss, a kid runs into the street and the vehicle, the car like just misses the child. Like what visual signal gave rise to that scenario? How can we learn from those scenarios? Unfortunately, those rare events happen quite rarely, right? 2.5 billion miles driven per event by NHTSA data, right? Like imagine you have a 100-car fleet, 20 cars seen at once in that fleet, right? You're driving average speeds for half the day, every day of the year. When would you see the first rare event if it happens once every 2.5 billion miles? And you're starting on January 1st. Well, you'd find it in the last week of February of the ninth year of work, right? So how big of a fleet would we need to get the thousands of scenarios of these rare events in order to train a model? Well, it's kind of an uncountable number. Or how many years would we have to wait? 40,000 years, right? Like, and that's with a 10,000 car fleet, for example, right? Like, we could resort to simulation. This is a little bit of an old, admittedly a little bit of an old simulation. Like things like Carla have become much more valuable, and in fact, AV companies are actually moving towards simulation more likely. However, there's a lot of bias in simulation, right? Like, and also like the sim to real gap is a challenge. Like, it's certainly not a solved problem, right? So, what did my group do to overcome this problem? Well, we went to YouTube actually. We were like, can we find a bunch of these rare events? Maybe, there's something like 40,000 years worth of rare events or driving data on YouTube, because people just like to post everything and anything on YouTube. And in fact, we found it, right? Like in the span of a month or so, we found more than 2,400 videos that had two vehicle crashes, rare events at junction crossings. They happen from different things, right? Like we annotated it for like hitter speed, victim direction, weather, time of day, all that stuff, right? And so this was becoming a data set. But what we realized is that, in order to actually make it useful for training autonomous vehicle models and planners and so on, we needed the 3D data, right? But these were like monocular cameras from the dashboard of these vehicles, but no 3D. Like and this was, 4 or 5 years ago, so predated a lot of the recent advances we've seen which would have arguable capabilities in these scenarios for reasons that I'll say in a second. But we don't have like the monocular depth estimation when we were doing this work. So what did we do, right? Like here, just simple problem. The first problem we tried to pose was, can we estimate the viewpoint direction, or equivalently the vehicle pose, from one view, from the bounding box in the egocentric view from the vehicle, right? So the input is a cropped bounding box around the vehicle, and the estimated pose is an output, right? So there was a method that we began with, called render for CNN, that did this exactly, and it gets decent performance on the order of 85 to 90% for vehicles and trucks and buses and things like that. And when we ran it in the data that we were working with, i.e., the car crash data, it just was out of domain, right? Or out of space, right? In some sense, right? Like the sample space or the state space is different. If all the training data was on good, undamaged vehicles, our test space here was on damaged vehicles. Doesn't work, doesn't transfer. So we weren't ready to throw out the problem. We didn't have the ability to go and get 3D data from this. We weren't going to use some of the sort of the pseudo 3D that you've seen in some other work over the years, like the human pose estimates in 3D, which are not really 3D if you don't have a appropriately equipped capture system. So what we decided to try to do was incorporate a human on the fly, right? So input image. Render for CNN works by extracting image features, computing some prediction layers, and then outputting the pose. This is just the pose for one of the angles. It's a bimodal distribution. What if instead we can get image features and prompt the human for a specific semantically meaningful key point? Like, what's the back? Can you click on the back left wheel? We call that a key point feature, right? That feeds in alongside those image features. And then as we learn how to predict, given both of those signals, a unimodal or a better prediction of the viewpoint estimate. Not that complicated, right? Take a simple AlexNet that feeds into a couple, fully connected layers. And we just augmented that AlexNet with what amounts to an attention-based mechanism, right? So like there's a pathway here in the network, which is where the user clicks. And then there's a one-hot vector, which is which of the key points were asked for. These are concatenated and then modulated to weight the confor. Obviously, in our experimentation, we tried to weight all the different layers and so on, and just confor tended to work best. And these are just led, and we retrained the prediction layers. So nothing that sophisticated, but it's a different way of looking at the problem. And we'll skip over this for time. And it actually works quite well, right? So like raw render for CNN is 84% on our data subset. If we fine tune it on just this subset, it gets about 86%. If we use our fully trained with, the network I just described for you, we can improve that by absolute 5%, right? Which is getting closer to usable. The metric here, by the way, is it's deemed correct if the accuracy is within pi/6 radians. This is not our metric. This is the metric from the Su et al. Render for CNN paper. So it works pretty well. Is able to handle much better situations like occlusion, where the render for CNN method's bimodal or even trimodal in certain scenarios, or truncation, which is a big deal in AV, especially like training data curation. But it does fail in certain cases, right? Like in this case, this front car is really highly occluding the back car. The model gets confused. I don't really know why it gets confused here, but it just has the motorcycle flipped. In this case, I don't really know what the vehicle is. The model didn't know what the vehicle is either. It's just a fancy sidecar doodad that confuses the model, right? So nothing's perfect, and it makes these mistakes, but it does improve the mechanism. But importantly, what we observed is that what's the horizontal axis here is like, basically think of it as like error in human guidance, right? Like as we increase the error, it goes right more on the horizontal axis, our ability to improve the accuracy, right? The blue bar here drops with the human guidance, right? So like we need the human guidance to be good in order for this human AI collaboration to be useful. It makes sense, but in science we got to study, we got to measure things. So we measured it. and it drops, right? So that got us thinking. This is a long-term project in my research group, so we've been thinking about this for a while. But we tried these scenarios in other situations like human guidance. We have some other prompting situations as well with language. But we ultimately started to identify this notion that humans are error prone. They're fallible, unclear, whether or not they intend to be that way, right? Like it's just our nature. We are not always correct in what we do, neither are AI systems, right? So we have to model that uncertainty in some way. So we began to codify this notion of humans as hazy oracles, right? So whereas the oracle assumption of, provides or assumes that all human provided information is semantically correct and unambiguous and equally useful, that ignores reality. That's not the way humans learn. It's not the way humans operate. It's not the way humans cooperate. Why should we assume that that should be the way robots or AI systems operate? Let's actually get out of the lab and get into reality, right? So what the old man's probably going to say is, get my mug. The robot's, maybe it's a new robot, or I don't know, this robot is in a nursing home or something like that, where it doesn't have a model adapted for this individual. It doesn't know what mug it is, right? So like, what is it going to do? It's going to bring him some mug, the green one. Wrong. So what happens in that case, right? Like the human information in that case was incorrect or ambiguous. It wasn't aligned with the features that the model actually learned, right? So in that case, the actual individual needs to rephrase the answer, but the individual shouldn't necessarily be the onus shouldn't be on the human to like know that it needs to go and program the VCR in a certain way, right? That would be the 1980s approach to the problem. Instead, the AI agent should actually be aware of what's happening and asks the human to rephrase the question. I didn't understand. Can you please rephrase that for me? Oh, get the orange one. That's mine. Hopefully, the next time the system learns on the fly and is able to adapt and actually recover, and so it doesn't have to go through this process again and again and again, which would be awfully annoying to the individual. But anyway, right. Succeed then. So there are some previous approaches to the notion of human error, right? One of those is just aggregating inputs, like instead of just having one human annotate data, you have 5 humans annotate data, and you take the max vote or the mean or whatever makes sense in the appropriate problem. But that kind of increases the cost, the time, the human need, and so on. It's really not a scalable approach. Um, and also, there are other scenarios where sort of like the context or the a priori definitions of what the actual answer is aren't actually aligned with the goal that's in the state space. And so you really have to look at humans and AI systems as a team. Like the data has to be good for the human to be able to answer. They have to understand the question. And it also has to be suitable for the computer vision or AI system to answer. And the mapping, that's like the language that the two use to talk together, needs to be calibrated in an appropriate way. I think, like selective prediction methods, which is the bottom left here, really um, only cover like the training time approach to the scenario. So we want to ensure that we ask the question, like, are humans and the AI, are they a good team? Is the input good for both, right? So let's just take one instance of that scenario, which is, can we determine whether or not to infer, which means we use the input the human gave us now, or should we defer, which means should we not use the human input? It's not good enough for us. Should we go and ask for another second input from the human? So we want to model that haziness, as we call it. And ultimately, we have a method that's called DARE, or dual loss additional error regression, that I'll quickly explain here. Right. So an ideal deferral function defers when the answer that it would get is incorrect, and the answer can be improved by a new human input, which is not always, because maybe the task model is just not up to snuff for the particular scenario. And so we introduced this notion of additional error, right? So we have Y, which is the target value, Y hat C, which is like the prediction with the candidate that from the received human input. And then we have this Y hat GS, which is the prediction from the task model given the perfect human input, which we'd never have at test time, but we need it at training time right now. We have an error metric L, which tells us sort of how good the target met the actual prediction, or sorry, the prediction met the target. So additional error is the difference in the loss from the gold standard to the prediction, right? So um, it can be improved. Like the closer to zero this number is, and it can never be less than zero. That's why that max is there. But it can be improved. Like the larger this additional error is, the greater the improvement that it can be possible. So ultimately, that also means the harder the task. So we're probably going to choose to defer when our additional error is pretty low, if that makes sense. Obviously we have to move from individual tasks, so, to whole data sets to be able to sort of compare metrics or methods. And so we also introduced this notion of the area under the mean additional error curve, right? So we have this notion of coverage, which is on the horizontal axis, which is the proportion of human inputs that are not deferred. So i.e., we will use on the right side of the graph, we will use all of the human inputs without any deferring, and then the mean additional error for that level of coverage. And we expect the graph to look something like this. And so we ultimately want to choose a method that has a lower area under that curve, because for any coverage, depending on the tolerance of the application, you may have a willingness to defer often, right? So we can't always say there's one answer here. That's why there's like this curve that we want to reduce the area under it. And so, the method is defined by kind of two key elements of where the error comes from, right? Like, first is like, what is the cause of the actual error, right? So in this case, on the left side here, the top row is the key point conditional viewpoint estimation error from the first part of the talk, right? Red here means that no matter what seed I get, right, like it's not going to help me at all, right? Like whereas on the right side of this, some seeds are better than others, right? Like if the area that's green, that means that I can get to a good convergence point for my inference if I get a seed somewhere in that green part, but not the red part, right? So there's this notion that some performance does depend on the seed, and a better seed would help. But there's also this notion of like the task model output, right? Like um, sometimes based on the actual data we have, a smaller error in the input space, like the image space, the red dot here versus the green dot's the gold standard. The red dot is a possible seed that's close to the gold standard in image space, but actually leads to a bad inference just based on the way the task model uses that seed. Whereas the yellow seed in the bottom right is actually quite far away from the gold standard seed, but it's still in that like convergence zone, the green zone, that can be used. Data is complicated. You really have to get to the nuances of data. And so our DARE method is rendered here, right? So we have in this case, it's for this other problem where you're trying to predict like the fine-grained scene classification. So you're given as input an image, and you're given a high-level scene category like outdoor versus indoor, and your goal is to predict like a fine-grained category like golf course or pool or things like that. So we have three different pathways from the data input on the left to the loss or model output on the right, right? The bottommost one is the actual gold standard, right? So this is what, given the gold standard seed and the model, and the image, you're going to go and predict what is my fine-grained scene classification. In the middle, you have the candidate seed and that same image with the task model. So you can kind of compute like a standard regression loss, right? Like, or even classification loss, depending on the problem. What's novel and what we want to learn is this rejection model, right? Like I'm given my seed, I'm given my model output, and I want to be able to predict whether or not I can like this is going to be a correct or incorrect output based on that seed. Again, without having access to the gold standard, because at inference time, all we're going to run the data we get through is the rejection model. And so there are two components of the loss. A binary like is, what is the cause of the error? Is it what we call correctness loss? And then what is the model's output? Like how good is the model? Like how much could we possibly improve the regression? And then we introduce this notion of expected additional error based on this formulation. And that ultimately has two parts, right? Like this probability that the seed is incorrect, which is the only case we care about. Because in the other case, if the seed is correct, then ultimately we would expect that the expected average error to be zero. So this term will just go away. And then we have the other term, which is the regression loss. And ultimately, we're going to infer if the additional error is low, and we're going to defer if the additional error is high. Actually, I think earlier in the talk I had that opposite, but this is the right way to think about it, right? Like, if the additional error is not going to, not that much from getting a new seed potentially, that's okay. Let's just infer now and save the burden on the human. Whereas if we can improve it greatly, then we'll defer. In the interest of time, I'll just tell you how this works sort of in practice, show you one result, and then get to the conclusion. So how does this work in practice, right? Like in situ, you'll have the input, you'll have the query, and then ultimately you're going to ask this question, do we expect the candidate seed to result in worse performance than the gold standard, or should we, expect some performance improvement? If we expect there to be some performance improvement, then we will requery and sort of restart this loop, and we'll be done. The two scenarios that we're talking about here, and I'll just give you some numbers, just it's meaningful. Like the improvement is meaningful and interesting, right? So like right here is the that area under the curve, right? Again, for dare against a bunch of baselines, right? Like a random defer or don't defer, kind of like a soft max response, which is essentially related to selective prediction. Other methods that we came up with, like entropy over the decision space and so on. In the mean case, the dare is the best case, like bolded means best, like lower is better in this case. But even more interestingly, the other cases that are sort of bouncing around, right? For the highest AMA, for the fold, just to us sort of implies that like some of these other methods are able to hone in on one type of error, whereas like dare is able to give you a good lowest per fold result, and that's why it's performing best for choosing to defer. Similar result in the hierarchical scene classification, and also for the situation where we're looking at the actual AMA or the actual curve in that coverage versus mean additional error for everything after point, I think it's like 0.19 or something like that, which is like an 80% deferral rate. In some sense, if you're willing to burden the user with a lot of deferences, then you can use any baseline that's built from first principles, and you'll get slightly better results. But that doesn't necessarily, imply you've learned anything. All right, so let's move through these, and I will get to the conclusion here. And thank you for your attention. So, the orange bit here is really the summary statement, right? Like this vector of work from my lab is really grounded in more than a decade of production and thinking, just to like drive toward this fundamental notion that if we really expect to have human AI collaboration, then we kind of need to reboot the way we think about how AI is trained and how AI operates and interacts in the environment. And ultimately, that's the message here. I just want to thank the sponsors for this work. This was sponsored by a bunch of federal funding, as well as like Toyota and Denso. And then just noting that most of this is open source and available. And if you're interested, there's a brief write-up of this research if you don't want to go to the technical papers on my Medium site. So thanks very much. I know I went a little bit over, Jimmy. My apologies, but it's good stuff. So hope there's a question or two, and then we can move on. Thanks.
Yep. So we'll include all the links in the follow-up. So no need to take crazy screenshots or anything like that. Jason, if you want to pop into the Q&A, it does look like there's a handful of questions there. Maybe you want to cherry pick a few and answer those live, and maybe the rest take offline and type your answers.
Right. Sounds good. So first question is, in autonomous driving, how is the distance between a car measured in order to maintain a certain gap to avoid collision? Well, I guess in AV scenarios, they're actually using metrically grounded distances. So like these would be from LiDAR, radar, or something like that. And that's why we needed to go from an ocular video, which has no notion of metric distance natively, to predict the actual distance. Let's see, let's pick another one at random. How does the deferral function assess the potential improvement in accuracy that can be attained from new human input? Yeah, so that's ultimately, if you recall the slide that had like the model on it, maybe I can go back to that. Let's see. this quick slide right here, ultimately we have to learn it, right? Like we can't actually, we can't compute it in a parametric way because on the fly, all we have are the task model, the primary input, and the candidate seed. We don't have the gold standard seed, so we can't actually compute like the relationship between, oh, how good is this candidate seed? So that rejection model is kind of like an observer. It's almost like a third party, and it's watching how for various candidate seeds, like it knows what the candidate seed is, and then the task model is fixed. So we're not training the task model at this time. It's kind of watching and saying, okay, for this input and this seed, how well did we do? Okay, and for that input and that seed, how well did we do? And like it doesn't have direct access to the gold standard seed. I don't recall if we actually sort of tried to map that in there, to push that in there. What it does get indirect guidance through the regression loss term here. And that guidance is used to really guide the rejection model toward an ability to reject or infer.